All right. So how much of yesterday's things about work do you guys remember? We guys got
If you give the terms, I remember everything.
terms, okay? No, work specific. Okay, like work is force into displacement, right? So what did we consider yesterday? Yeah.
Intensity factor into capacity factor.
Huh.
That is your
Oh,
displacement basically.
Yeah, force into displacement. Abhi we are looking at mechanical work done by this particular piston. Um,
Ma'am, I had one doubt about work done itself. So the formula is F dx, right?
yeah.
And then you told in terms of like if we do it in terms of this, so it
Yeah.
will be, I think you said pressure into area into length.
Area into length is volume.
So could you just rewrite the formula? Then I might have copied it wrong.
Yeah, just a moment. So this is P external hai. This like black is, let's say, like initial condition. What I'm putting in blue is final condition. So I'm applying P external pressure. It's gonna move until the side under B, the pressure is P external. Okay. So force applied F will be equal to area of cross section will be A. So these are the things that we wanted to know. L. So the volume, like when it moved, like the difference in volume, initial volume minus final volume is delta V. Okay. So what is the force? See, if the external pressure is P or PEX, what is the force that is applied? Work calculation के लिए force चाहिए ना?
External
Pressure
into area.
area of cross
हाँ,
P
pressure
X into it.
to area. Okay. So pressure is force per unit area. So force will be pressure into area. Next, difference in volume, delta V is equal to,
Area of cross section into L.
correct. Yeah, so this we'll rewrite it as L equal to delta V by A. So work, so yesterday what we saw was work done in single step. Like पहले V initial था, बाद में V final हुआ. So what was the work done? So work done, this is in one step. Like if this change happened in one step, so that is irreversible. एक step में हुआ मतलब it's not like tiny changes happening. It happened in one step. So W irreversible is equal to, if we have to do the derivation, force F dx. So applied here, force is P external into area multiplied by dx is displacement. So that is equivalent to L. So L, I'll take it from here, delta V upon A. So area gets cancelled. That is equal to P, like pressure into the change in volume. That is P into V final minus V initial. Okay. So because P is an external thing, work is being done on the system. We are adding energy to the system, right? To this whole thing inside. So V final minus V initial. So this whole thing will be a positive value or a negative value?
Positive.
Positive value.
Positive.
How?
Work is done on the
We are
system.
applying force.
Because we are giving it extra energy. So the final will be more than
like
the
यहाँ पे
initial.
positive होगा, but consider like numerically, mathematically, what value will you get? V final minus V initial क्या है?
Negative value.
So ये negative हो रहा है ना, but because we are considering from the point of view of the system, overall positive value होना चाहिए. So the correct formula will be always when you consider work, that will be equal to minus P into V final minus V initial. Okay. So the logic is this: when I take f dx, mera f is a positive value because conventionally I'm considering agar left to right hai wo positive hai. But when I take it from the point of view of system, it is exerting like equal and opposite इस तरफ हो रहा है ना, so pressure का direction reverse हो गया, like from the point of view of system it's the opposite of that. So that is the reason I am adding a negative sign over here to make it correct as per our convention. Keep it.
Ma'am, what is IRR or whatever you wrote below W?
Oh, so to represent it's a irreversible process. Like एक step में I'm just pushing it, so that's an irreversible process. We have done this yesterday, you guys. Just check your notes from yesterday. If you've already noted it down, you don't have to do it again.
We already.
करना है तो you can correct it. One extra thing noted down, so this should be a negative value because we're considering system and work is done on the system, तो positive होना चाहिए. To make it correct in every way, this is negative times negative, overall we'll get a positive value as per our convention. So this is when we're doing it in one step. Okay.
Ma'am, is it possible for you to just repeat what did you say it would be in terms of the system?
See, when work is done on the system, as per convention, should it be negative or positive?
Positive.
Lekin if you calculate it numerically, V final minus V initial, ये हमें negative value आ रहा है कि positive value?
Negative.
But it needs to be positive ideally, no? So that's why we're multiplying it with a minus. So that's like the mathematical reason behind it. Logically speaking, you're reversing the direction of pressure because what we've taken here is from external point of view. So if you are looking at it from the point of view of the system, whatever is inside, it's in the opposite direction. Isliye P is multiplied by minus. That's the conceptual or the thing, logical reason. Justification. That's it. Okay. So we'll go to the reversible process case. Do the drawing. What's up, Kaveri?
You go back just a second.
So this is something that we've done yesterday only, Kaveri. So you can check your notes from yesterday. If you just compare it, if you've written everything down, theek hai. If not, just make those modifications. You don't have to copy it all.
Done, ma'am.
Okay. All right. Same thing. I'm just like drawing this because apparently I can't copy paste images from one thing to another. Same. Okay. P external aa raha hai. So this is the area. final case mein the piston is over here, volume is reduced. So this is the initial, this is the final difference result, but we don't have to worry about this part. Okay, so second case, if it is not happening in one step, like basically it's happening in multiple steps, it's a reversible process. So reversible process matlab there is tiny changes taking place there. So what then?
Could you repeat?
So this is the second case, is the pressure, like if it is achieved in many steps. So if it is done in many steps. So pehla tha, if it is done in one step, this is the first case. One step matlab yahan pe tha, fir it has been compressed to this much. Ek step mein piche gaya. This is when it is done in many steps, matlab yahan pe tha initially, then it was brought till here, then it was brought till here, then it was brought till here, and when finally it is brought till here. So it happened at multiple steps. So in this case, initial pressure that you applied was PEX, or let's say internal pressure, let's say this is P internal. So pehle jab yahan pe tha, so it was P internal. Finally, when it came here, P internal should be equal to P external. But when it is done in many steps, it's like, remember yesterday's example, like let's say it was at 1 bar and we have increased it to 2 bar. Pehla method tha just like going from 1 bar to 2 bar, just like that. This case is basically going from 1 bar. Then when you're reducing the volume a little bit, this becomes 1.1, and then it becomes 1.2, then it becomes 1.3, and then it's going on in so many multiple steps. So the change in volume is being accompanied by the change in the pressure also, right? So then how do we calculate the work done? So then work done, it's essentially going to be the same. So work done, in this case, it is W reversible. Same thing, like F into dx. So F is going to be the pressure into delta V. So that's what it's going to be. But it's not as simple as delta V is not simply final volume minus initial volume, because there's like a tiny change in volume taking place. So instead of delta volume, in this case, this is going to become PdV. And this is going to be integral of the pressure into D.
Ma'am, I have a small doubt. How come if you even go from 1 bar to 2 bar directly, you can't change it back to 1 bar?
No, then that will be a completely different process. Then you'll have to, then the system will do work on it.
But even in the reversible process, if it attains like P external is equal to P internal, then that also becomes irreversible then, right?
Again, focus on the path. Work is a path function. The way you do it matters. If you do it in such a way that you do it like in really tiny increments, it is reversible. Like you can reverse the direction at any point. Like a tiny change in the conditions, like the conditions inside is able to reverse the direction. Going from 1 to 2 bar, it's like 1 bar tha, uske baad abhi 2 bar ho gaya. Like you've gone to the final step, like final condition in one step. Like, how do I reverse it? Like, I can't do it as it just happened. That's it. But reversible may, because you're going like in tiny steps, at any point a small change in the conditions over here, like thoda sa temperature increase kiya, then it's gonna push it backwards. If I add some more gas, like number of molecules change hua, it's gonna push it this way. So any tiny change in the conditions is capable of reversing the direction.
Also, the reason you're using integral here is integration, sorry, is
Mhm.
because you're actually taking the average, right? Or something like that.
Average nahi. So integral is so the work done in changing like from here to one small dv, then second dv, then the third dv, then the fourth dv. Like I'm summing up all of these together. So that's what integration is. So like moving from here to here would have taken some work. Then from here to here would have taken some more work. Till here is some more work. Till here is some more work. So I'm adding up all of these tiny amounts of work. So that's what the integration is.
And ma'am, why the negative sign?
Again, from the point of view of the system. So this like system is
Oh,
applying.
okay, same as before.
Yeah. Yeah. So we
Can
are.
you do one sum about this?
Yeah, so this is not the end. Like we're still deriving it. Abhi ye integration pura karke we need to get the final thing. So the integration is from initial volume to final volume. So this will be from Vi to Vf. Okay, so PdV hai na?
Excuse me, ma'am.
Yeah.
What happened to dx?
No, it is force into displacement. So displacement, we wrote it as dV upon area. Force, we wrote it as pressure times area. So that area got cancelled.
Oh, okay, it got cancelled.
The funda is the same as this thing, except because that was in final step, it was simple for us. Like, pehle initial tha, fir final ho gaya. This is the only thing
Yeah.
to worry about. But because it's like infinitesimal change, tiny changes, we are having to add all of those tiny changes. That's why the integration comes into picture. Okay, so abhi, as our volume is changing, our pressure is also changing from P external to P internal, right? So basically with each step, the internal pressure, like, so the P external is equal to the P internal plus or minus dP. This doesn't make any sense. I think it should be, so the internal pressure, the pressure that's faced inside, it is changing. Like initially yahan pe P internal tha, it is going in until it becomes P external. So with every tiny change in volume, the internal pressure is also changing. So if we assume like dV change in volume ke liye dP change in pressure hua. So the P internal is P external plus or minus dP, depending on which direction it's going in. Right? So work, so W reversible can be written as minus integral Vi Vf. So this I can write it as P external equal to P internal plus or minus dP. So P external plus or minus dP into dV. So that'll be equal to,
Why plus or minus? We know like the pressure is increasing, right?
increasing because we assumed that, okay, this is like going in inwards.
But it would only go inwards if the external pressure is more than the internal pressure.
Keyword being if the external pressure is more than the internal pressure. If it was the other way around, then the signs would be reversed. That's why plus or minus. It can be either plus or minus depending on P external. Okay. So that will be equal to integral Vi to Vf.
Ma'am, I don't understand the P internal is equal to P external plus minus dP. Could you explain that?
So like as the volume is changing, the pressure also will change inside.
Yeah.
So that's what I've expressed it as, like for every dV change in volume, I'm assuming there's a dP change in pressure. So at every step, the P internal is equal to, like basically P internal is changing by dP until the internal pressure becomes equal to the external pressure.
In which direction is the piston going though?
That depends on whether it's like P external is greater or lesser than P internal.
So whatever it is, we just need to make the two equal, and that we'll do by adding or subtracting dP.
We are not making it equal. I'm saying, like, again, it's happening in multiple steps, right? So with at every step, there is a change, dV change in volume. At the same time, there's a dP change in pressure.
Sorry, ma'am, you hung in the middle. Could you repeat?
Can you hear, like, am I audible now? Is it better now?
Yeah.
So with every dV change in volume, there is a dP change in pressure. So अगर initially P internal था, तो फिर P internal plus dP plus another dP plus another dP. तो वैसे it keeps changing.
But the whole point of it is so that P external and P internal become equal, right?
Yeah. So it will keep changing until P internal is equal to P external. That's the point.
Yeah.
Like, it's not happening in one step, it's happening in multiple steps. So
Yeah, asking that depend whatever direction it is, that will depend, and or the if we're adding or subtracting dP would depend on whatever direction the piston.
correct. Yes.
Yeah.
Okay. So this, like,
Ma'am,
yeah.
could you like explain again, like how did you, I mean, rather, why did you in the first step you wrote pressure internal is equal to pressure external. For the second step, you took it as pressure external is equal to pressure internal. Could you say that? Like, could you explain it again? What you did over there?
I just rearranged it. Like basically the internal pressure will keep changing until it is equal to the external pressure. Or just ignore all of this. The point is the internal pressure will keep changing until it's equal to the external pressure, right? So I can just write this as P internal either plus or minus depending on the direction dP into dV. Yahan tak clear? Like, understood?
I have one doubt.
Hmm?
Like, is this like the general formula? So, like, if the piston is like moving inwards, we use like addition, and if it's moving the other way, we use subtraction, or like on each step, it depends what the value is. And as soon as like P internal is equal, like we stop adding. I didn't get that part.
Yeah. So like if it is moving inwards, we know that by logic, common sense, volume decreasing, pressure increasing. So at each step, there is dP being added to it. So this will be P internal plus dP. So if it is moving outwards, we know that, okay, volume increasing, pressure decreasing. So it will be minus dP at each step. This I'll write as P internal times dV plus or minus integral Vi to Vf dp into dv. Okay, now there are two things you need to look at here. First is P internal. So under gas hai na, so I have a relation PV equal to nRT. So I can write my pressure in terms of nRT divided by V. Right? This is all P internal because we are considering volume of the gas, pressure of the gas. The second expression, dP is a tiny change in pressure with dV is a tiny change in pressure. Think of it in terms of 0.00001 meter cube change in volume, 0.0000001 bar change in pressure. So multiplying dP by dV is going to be an extremely tiny value that we can neglect it. So this is so small, it is negligible.
So it's fine if we don't write the second expression, right?
Yes, it's almost equivalent to 0. You can, like, for all practical purposes, you can take it to be 0 only because dP and dV are extremely tiny changes. So what will be left with is minus integral Vi to Vf. dP is nRT by V dV.
Could you please explain this step again?
What part in this step, Kaveri? Like the first expression or second expression?
The second one.
So dP is an extremely tiny change in pressure and dV is an extremely tiny change in volume. So we're taking tiny steps here. So assume it's on the scale of 0.0000001 meter cube change in volume. And these are just hypothetical values I'm taking. Like whenever we get differentiation integration in our mathematical calculations, we are looking at a really tiny change, be it physics may like change in displacement, change in velocity, or in this case, change in volume, change in pressure. Now, when I multiply numbers on this scale, if I try to calculate V into P, what sort of a number am I going to get, Kaveri?
A really small one.
It's extremely small, so small that we can neglect it. It's practically equal to 0.
Is dV also very small?
Yeah, wherever you find D, it means it's like really small. So if you find dx, very tiny change in the displacement, even less than a
Then
millimeter.
for the
Really?
for the first statement, like P internal into dV, in that also the value would be less only, right?
It'll be really less, but we are adding up all these tiny drops. Like this is integral of pressure, like even this factor is there. Yahan pe we are neglecting it because it is practically it's dP times dV. That makes it like exponentially smaller. That's why it's okay if we neglect it. But we cannot neglect this term, we cannot neglect this term because you have this value also. This is kind of substantial, which is why we'll be able to integrate this.
And ma'am, I know you said it before, but why are we taking it minus?
Again, from the point of view of system, pressure is in the opposite direction. So minus. And it also fits
Okay.
with like our conventions regarding work also. Work done by the system, work done on the system. Okay. So integral V initial to V final, nRT by V dV. This is what we got in the previous thing. So 1 by V dV का integral क्या है? Have you guys come across this integration before?
It's undefined, right? It'll be 0 by 0.
Huh? No.
Of what again? Could you repeat?
Integral 1 by x dx अगर ऐसा है तो what is the integration of this?
X raised to 0 upon 0.
Huh. Like, okay, you guys haven't come across this. You've only done regular, like, you've done x dx and similar ones. This one you haven't done, yeah?
No, not in
I
particular.
don't think we've done 1 by x. Like we've done 1 by x squared.
Okay. So this you guys haven't done. Okay. So I'll tell you what it is. When you have 1 by x, you can't use your normal rules because as Ritu said, you get x power 0 by 0, which is undefined. So integration of this sort of a thing, then you get into logarithms. Minus nRT, n, r, and t are constant because we are like number of particles of the gas is not changing, temperature is not changing. This is a universal constant. So integral v dv, this becomes logarithm of v, and this we need to sum from vi to vf. So basically this becomes minus nRT logarithm of v final minus logarithm of v initial. Okay, so integral of 1 by x dx is log x. Similarly, when you differentiate log x, you get 1 by x. And if you recall the rules of logarithm, this becomes minus nRT logarithm of vf by vi. So this is the expression for work done v reversible. Oh, sorry, my bad. You won't get log, you'll get natural logarithm. So log means the base is 10. So this is the base is e, natural logarithm here. So if we want to convert it into regular log so that you can do calculations based on this, you multiply it by 2.303.
Ma'am, I did not understand the log part.
So you guys have you done logarithms like math mein or physics mein?
No, we never done it on the.
You don't have logarithms.
No, I mean we had an equilibrium also today. Ma'am was teaching. I didn't understand that. We have logs.
I'm
Yeah.
talking about logarithm as like jaise
As a
math
whole.
mein
We
have
don't have it in
addition,
maths.
No,
addition,
ma'am.
subtraction.
I
वैसे
know how to see the table, but I don't know how to like find.
I only knew the log x one thing because that itself made us right, but otherwise, like the whole concept, I didn't get it. Like today also we had equilibrium. We are solving questions.
yeah.
For us, ma'am told we mostly won't get any log questions.
Like if you're not allowed to use calculators, log tables, then there's no point giving you logarithm based questions. So okay, conceptually you guys have never come across log like functions mein aisa kuch math mein bhi nahi, you haven't come across it. Okay.
No.
No, ma'am.
So like addition ka reverse is subtraction, right? Oh, Kaveri's done it for applied math. Cool. Okay. So you have worked on logarithms and familiar with the concept. That's good. That's an advantage you have there.
They just taught us table and yeah, and anti-log and stuff.
Okay. So जैसे addition का subtraction होता है, multiplication का inverse division होता है, like 2 into 3, 6. इसका reverse, like 6 divided by 2, you get 3, or 6 divided by 3, you get 2, right? It's like reverse. Similarly, whenever you have exponents, suppose you have a raised to the power n equal to x. Iska inverse is logarithm. So this I can write it as logarithm of x to the base a will be equal to n. So it's the relation between the exponent and the result. So agar n exponent hai for the base a, x is the result, तो उसका inverse, kind of like inverse function. So if I take logarithm of x to the same base, then this becomes, that will be equal to n. So that is logarithm.
Ma'am, so I think today itself our chemistry ma'am was doing it. So is it like ma'am wrote 10 to the power minus 3 and then below I think log 10 is equal to 3. So is it like something like that?
Yeah, so that's what, like you take specific values. So easy concept ko if I just expand it. So if I have 10 raised to the power 3, what is this equal to?
3.
10 raised to the power 3, guys, क्या है ये?
1,000.
1000.
I'm saying 1,000.
So if I take log 1000 to the base 10, what will this be equal to?
3.
3.
There you go.
3.
That's what it is. So logarithm, just like how you have laws with exponents, right? You have a power m into a power n equal to a power m plus n. You have a power m divided by a power n equal to a power m minus n. Like, ये सारे याद है? So same thing, you have certain things with logarithms also. You can see it's the exact reverse of it. So if I have log a plus log b, so that will be equal to logarithm of a into b. So you can see, like exponents mein case mein, if I'm multiplying two exponents, I can add up those exponents. Uska reverse hai, when I'm adding the logarithm of the exponents, I can like basically multiply them. The only,
What does the value actually give?
what do you mean?
Like the one we like got just 3. So what does that signify?
So it's just a function, just like how you have sine, cos. That way, this logarithm is a function that deals with exponents. The primary reason why logarithms exist is to make calculations and things easier. So that's the reason you guys have like log tables and all of that. But I think now it's going out of fashion. Like you guys are not being taught about it and all that because calculators exist. You can just press log this and you can get it. But a lot of physics and chemistry are, you can see a lot of formulas and all. When you use differentiation, integration and all, you end up getting logs. So if you're not like taught about the functions at all, it's going to be kind of difficult for you to follow. That's what I don't understand how to deal with.
No, like we did log questions in chem, but like our teacher, like he just solved it and he's like, you guys just like see it and learn and stuff. But like he used calculators and log tables. How are we supposed to do it in the exam?
See, if you're not expected to use calculators and log tables, you will not get questions giving log. And even if you do get questions, question ke end mein brackets mein you'll be given. So use log 2 equal to so and so value, log 3 equal to so and so value, वैसे करके.
Ma'am, we have logarithm in like 12th class maths.
Functions, relations, functions में क्या?
That I don't know, but yeah, I think our sir was telling we will have it in 12th class.
See, 12th में 75% of your maths is going to be differentiation and integration. Usme there's like a list of functions that are quite important that you need to know. So apart from your regular polynomials and all, trigonometric functions ke differentiation, integration you need to know. And there are two specific things. So one is logarithm. So when you take, so यहाँ पे base है ना, यहाँ पे base 10 है, base a. So base can be any number. But specifically, just like pi, there is another number called e. Jiska value hai 2.7 something something. I don't remember the exact value. But e is like another irrational constant number. Like how you have pi equal to 3.14, e is another value. So when you take logarithm to the base e of any number, so this is called natural logarithm. And the result of like integration differentiation हमेशा natural logarithm होता है. So that is represented because natural है, it's represented as ln, ln. So, but in your calculations and all, like calculators may, like practically speaking, ln use नहीं होता है उतना. The most commonly used logarithms, be it log tables or in calculators, is log to the base 10. So that is why this conversion, like when you want to convert natural logarithm, like log to the base e into log to the base 10, you multiply it with this particular number, 2.303. So 2.303 is going to be like your best friend in physical chemistry. So whenever, whichever concept, जैसे यहाँ पे logarithm है, equilibrium में logarithm में होगा, chemical kinetics maybe you'll have like logarithm based things, electrochemistry maybe a derivation has logarithm. So wherever you come across that, this number will always be there.
So, ma'am, 1 by x dx is log x.
That's a mistake I did. It's natural logarithm. So ln x होना चाहिए, which is equal to 2.303 times log x. Logarithmic function है, just that the base will be e. Similarly, along with trigonometric functions, logarithms, you'll have differentiation integration of e power x also. This is a specific function. Yeah, Kaveri, what's up?
Could you explain this 2.303 thing again? I don't understand.
I don't know the logic behind it. So basically, if you want to convert logarithm to the base e into logarithm to the base 10, you multiply by 2.303. It's a conversion factor. You can take it like that.
E.
E is a constant. Like how pi is a constant, 3.14 karke, that way E is another constant in mathematics.
And the value is 2.7.
Something,
is it?
something. I'll just Google and find the exact value.
But why do we need to convert 2.7 ka log to
Practical purpose, because if you look at your log tables, if you look at your calculator, हमेशा logarithm है. So the default is log to the base 10. So if you want to apply that in your calculations, you need to bring it to log to the base 10. You don't
how
have-
do we know that tab will always be log e?
Because that's the rule, that's the principle. Integration करने के बाद you get log to the base e.
Oh, acha.
There you go. The value of e is, oh nice. So it's called Euler's number. I'll just show you the details about it. There you go. It's the mathematical constant, 2.718218. So on. This is the thing. And this is the expression for e. So that's limit n tends to infinity, 1 plus 1 by n raised to the power n. That's the thing.
Ma'am, I have a question.
Hmm?
So, wait, how did log come into our derivation?
Oh,
Can
again,
you just go with that?
yeah. Use a different color for highlighting. So, right. So this is our integral, right? So integral
Yeah.
minus nRT is a constant, so ignore that. Bahar leke aao. You have dv upon v. So iska integral is natural logarithm, like log to the base e of v. This
Oh,
is-
okay.
yeah.
So, like when we integrate that, we'll get log, like natural log.
Yes.
Okay.
Okay, so all of this is just explanation, like noted down in rough, or if you want, you can note it down somewhere else. Main thing is, see that you've written down everything that I've done in blue. So this integration. So whenever you integrate it from one value to another value, what the subtraction ho jayega, right? Like from here to here. Then using the rules of logarithms, this becomes ln of vf divided by vi, or if you want to take it in natural log, so W reversible is minus 2.303 nRT log Vf upon Vi. This is the final thing. Okay, guys, tell me when you're done noting, then we go to the next part. Five people done, okay. So Rishit, Sanskriti, and Kaveri.
Ma'am, I'm done with this. Could you just after this, after we are done, could you just go back to the previous slide and just take a screenshot?
So we are using integration here to add all the small differences, right? In the change in basically the change.
Correct, yes.
Sometimes we also use integration for the average too, right?
No. Average matlab you sum it up and then you divide it by the number of things. So integration is sum of. So average find out karne mein you there is like a component of summation, right? So if it's in that context, maybe, but integration is never equivalent to average, like it is summation. Okay. So there's a specific case of work, like what if the expansion, say there's something called free expansion of a gas. So free expansion, you can think of it as diffusion. Like for example, I have an oxygen cylinder, oxygen tank here, and then I just open the nozzle a little bit. So if there's any sort of a hole, gas is going to like diffuse out of it, right? High pressure, say, like it's going into a low pressure area. But it's going because there is a hole, and like it's a tendency of gases to occupy whatever space they get. In that case, what do you think is the work done?
So there is like a bottle and
No
there is a
work
hole in
done?
it.
Ritu said no work done. Okay.
Ma'am, by the system.
Yeah.
What is the question? Like there is just a hole in a bottle.
Yeah. Like when a gas expands on its own. Like for example, let's say you have a vacuum chamber, and then like you just attach a small hole in that vacuum chamber. Then obviously air is going to rush inside this thing, right? So in that sort of a situation, what is the work done?
Is the work done like reversible or irreversible?
Whatever the case may be.
In the case of the piston, were we applying external force to it, or was it just happening on its by the system?
Can you repeat that, Kaveri? What?
In the case of the piston that we just did, was external force being applied, or was it just being done by the system?
There was a difference in pressure inside and outside. Like that's the thing. There is an external pressure being applied. Like if it is greater and it's being pushed inside, if it is lesser, then it'll be pushed outside. So Ritu and Rishit, you guys, like Ritu, your first answer is correct. So work done is 0. Okay. So in the situation where there is free expansion of gases, like when it's expanding against a vacuum, like when there's no, when it's not like pushing against like a certain pressure, or if there's like, if it's, yeah, whether it's like, whether the external pressure is higher or lower, whatever the case is, if there is free expansion of gases where it's like the, if the expansion is happening purely due to the tendency of the gas, like diffusion, in that case, there is no work done by the gas, that sort of a system. Okay. Because the reason is that, so the P external is basically equal to 0 because it's expanding into a vacuum. Vacuum matlab there is no pressure being exerted there whatsoever. So that sort of a situation, P external is 0, so work done also becomes 0. So free expansion of a gas matlab you can note down. So if gas expands on its own, like in vacuum, then work done will be equal to 0 since P external is 0. So that sort of a situation is called free expansion of a gas.
Excuse me, ma'am, I have a doubt. So, like, if gas will expand freely in a vacuum, and since space is like vacuum, then why don't like planets like Jupiter just disappear?
Gravity.
Because they are gas giants, right?
They are gas giants. The reason why those gas giants even formed in the first place is because of gravitational force of attraction. If gravity didn't exist, you're right. Like all of the gas is just free to diffuse off and goes off.
So, but like, what holds the gas together?
Gravity, force of gravitation.
Oh, like if we just leave helium, like a bunch of helium together, like a bunch of helium atoms, it won't just stay together, right? Like, it'll diffuse, obviously. So, like, how do planets stay together?
Force of gravitation. So that is the reason Jupiter, Saturn, all of these are able to hold on to it because their gravitational force is enough to capture it. But hydrogen, helium, you will not find it on Earth. Like once hydrogen and helium are let out of like tanks or cylinders or any sort of restrictions, they will not exist on Earth. They will escape off because the force of attraction of the Earth is not enough to hold on to those masses. That is why Moon doesn't have an atmosphere. Like humans have gone, there have been like spaceships going there. Even otherwise, like Moon was formed from like parts of Earth, right? Like still there is no atmosphere because its gravitational force is not strong enough to hold those gases. Like all of those gases have diffused off because of free expansion. Yeah, Ritu, what's up?
Isn't like force between gases supposed to be like the weakest between all solids? How is like Jupiter so big then? And also if we take like a giant fan or something, like if we manage to like spray the molecules a little bit, like can we destroy Jupiter or something?
Theoretically, yes. You just need to figure out how big of a fan you need to blow all of that around. I'm just gonna Google size of Jupiter just to give you guys an idea of the scale.
I think it's 30 times Earth.
Apparently, you can fit like 130 Earths in it, something like that.
It's definitely it's more than Earth, I think. Like more than 30 Earths.
There you go. Oh, Earth and Mars is conveniently given for reference. So you can see Earth is 6 into 10 power 24 kg. Jupiter is almost 10 power 27 kg. So Jupiter is 1,000 times heavier than Earth. So gravitational force, even if you apply that g/m by r square, the force is at least 1,000 times stronger than what would be.
Wait, so like it's about 1,000 times more than Earth and it's only gas.
How will
Yeah.
you land over there?
Not
then? It's
just
just
gas and
You can't land on it, now you'll just go through it.
Juno spaceship, that's what happened, no? It was revolving around Jupiter, getting all of that data. And then once its fuel got over, it fell into the gravitational orbit of Jupiter. It just like spun round, 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 round until it fell inside Jupiter. So check it out, like Juno spacecraft. So it still like, let's see, and
Is it still like orbiting?
I know the last I remember, I think it operational components timeline. Let's see. Launched. Okay, orbit. End of second mission extension. Okay, do some research. Like now we're like eating up into the time. But yes, all these spacecrafts and all, they've fallen inside. Like there's no place, like you can't go to Jupiter because there is no place to like stand anywhere. It's all gas. It's similar to a star, but star may you have active fusion reactions and all taking place. That's why stars twinkle and they give out heat, light, and all. That doesn't happen with the gas giant planets. They're just like held together with gravity. That's it.
Yeah, I heard somebody say that like planets like Jupiter and Saturns are like failures of stars. Like
Yes.
they aren't big enough to become stars,
Yeah.
but they're bigger than the average planet.
Yeah.
So, ma'am,
How
if
come
we
the
were
gas-like stuff
to,
is bigger?
How come what?
The gas, like all the bodies made like out of gas are bigger.
They just aggregated more. That goes into astronomy. They just form that way, like a lot more particles have aggregated together in the gas giant, so it happened.
so ma'am, the Jupiter is just kept together because of the gravitational forces.
Every single thing in the universe, be it a star, be it a planet, be it an asteroid, like they are matter because they've come together because of gravitational force. Arnav figured it out. Okay, Galileo was the one that went through Jupiter. It wasn't Juno. Okay, I got my satellites confused. Right. So Galileo is the one that collapsed and it went inside Jupiter. Yeah. Cool. Okay, let's come back to thermodynamics. Free expansion, so that happens. Okay.
Like in a vacuum, what does that mean? Like outside is there a vacuum, inside is there, what is it?
So if it's expanding into vacuum, so there is no external pressure pushing against it. So work done becomes zero.
Like the cylinder is kept inside a like a vacuum room or something.
Huh? Like a what?
So the cylinder is kept inside vacuum.
No, so like gas is let inside a vacuum. So think of it as like the situation Sanath has mentioned. Like if some gas was just let out in space, like if there's a oxygen tank explosion in space and all of the gases from the tank it's expanding into space, or let's say there's a vacuum chamber, like you created a vacuum chamber, emptied it of air because you want to study a specific gas or something, then you are filling up this vacuum chamber with that gas by attaching a nozzle or a pipe leading into it. So then whatever gas is coming inside here is expanding into the vacuum that is inside this chamber. So many different possibilities, situations possible. But basically, yeah, when it's expanding into a vacuum without resistance, like without an external pressure. Okay. So work is this. Work is like the measure of heat or measure of energy against like a certain pressure, against, when there's like expansion, contraction going on. Another path dependent function that we look at is heat, denoted by Q. Heat is pretty simple, straightforward. It's its own thing. It is the form of energy, which is heat energy. So this particular measurement, like this particular energy is it's the quantity of energy that is either absorbed or released on the account of temperature difference. It is like what you guys understand by heat energy, like that's the heat energy, like something that comes from fire, something that you can feel, makes you feel hot. That's heat energy. It's represented by Q. Again, just like work, if heat is transferred from system to surroundings, when system is losing heat, then it is, so Q is negative. And if it is being transferred from surroundings to system, when the system is gaining heat, then Q is positive. These are the sign conventions. So then you have heat, like heat capacity and all, you guys haven't studied, right? Heat capacity, specific heat capacity, okay. So those are like some calculations and measurements and things specific only to heat. So just in short, like heat capacity is what amount of heat energy is required by a substance to increase its temperature by so many degrees Celsius or so much Kelvin. So that's, so agar zyada, if you want to increase it by so much temperature difference, you need a lot of heat. So directly proportional hai. There's a coefficient involved with it. So that's like specific heat capacity, things related to that. But yeah, basically heat transfer related things is what heat capacity is. Yeah. So now like let's get into proper thermodynamics. So there's something called zeroth law of thermodynamics. The reason why it's called zeroth law is because people have proposed, found out, put out first law, second law, and then somebody proposed the statement and they're like, wait, this is more fundamental than the other things we discovered. So first se bhi zyada hona chahiye. So that's why it came to be called as zeroth law of thermodynamics. It's only because of the timeline that it's called zeroth law. So zeroth law of thermodynamics is very, very, very simple. So it basically says that, let me look for the statement first.
Ma'am, I kinda got disconnected. Could you just go back one slide?
We just discussed heat. So heat is like what you understand by heat energy, something that makes you feel hot, contributes to temperature difference mainly. And convention related to heat, variable that you use is Q. So if you transfer it from system to surroundings, system is losing heat, so it'll be negative. And if it's the other way around, when system is gaining heat, it'll be positive, just like work. Okay, zeroth law of thermodynamics. Okay, this is the statement. If each of the two objects is in thermal equilibrium with a third object, then they are also in thermal equilibrium with each other. So basically what it's saying is, I'm going to write it in like really crude, rough way, easy to understand way. Okay, this is not the formal statement. So let's say we have three objects, A, B, C. Okay, so if A is in thermal equilibrium with C and B is also in thermal equilibrium with C. So here the relation, like with the arrows, what I'm defining is thermal equilibrium. Then
What is the meaning of thermal equilibrium?
that's what I was going to ask you guys. Equilibrium word hai. What sort of sense do you get from the word equilibrium?
Equal amount
Equal.
of energy. So like equal
Heat
amount of
energy is
temperature.
equal.
Equal, sort of, right? And we're talking about thermal equilibrium.
So the heat difference
So
is equal.
same, both objects are on the same temperature.
There you go. That's what thermal equilibrium means. So equilibrium nahi hota, then the hotter one is going to give heat energy to the colder one. So that's going to keep happening until both are equal. So equilibrium doesn't mean that they both are not exchanging heat, just that whatever heat is A is giving out is equal to the amount of heat that C is giving out. So, like for our calculations and all, the net difference is zero, whatever heat exchange is going on. So the process is still going on. We just can't see it because whatever A is getting, it's giving back. So the net is zero. So A is in thermal equilibrium with C and B is also in thermal equilibrium with C. Then what can you say?
A and B are in
A
thermal
and B are
equilibrium.
also in thermal equilibrium.
A, B, C are also in thermal
There you go.
equilibrium.
Correct. Then A and B are also in thermal equilibrium with each other. That's what zeroth law states. That's what it is. Okay, so I'll repeat the statement again. So if, yeah,
I still don't understand the meaning of thermal equilibrium.
thermal equilibrium means they're at the same temperature. Like the amount of heat exchange going on there is the same. Like jitna bhi heat A is giving out, C is also giving out the same amount of heat energy.
Okay.
So if each of the two objects is in thermal equilibrium with a third object, so hamara two objects are A and B, each of them is in thermal equilibrium with our third object C, then they are also in thermal equilibrium with each other. So A and B are also in thermal equilibrium with each other. So maths you guys have read, no? If A equal to C and B equal to C, then A equal to B. You've used this lots of times. Same thing applied to this. Ritu is asking, does thermal equilibrium means Q of A is equal to Q of C? There's a little bit of fallacy in that, Ritu, because Q is a path function. So you can only figure out how much heat energy is given out or taken in. You cannot measure the heat energy at this point of time. Like at this point of time, ye cell phone ka heat energy kitna hai? Like that is something that we cannot define properly. Yeah. So heat energy can be given or taken out, like when I light a fire, when I expose it to radioactive something, or any source of heat basically, or when I expose it to a hot object. But specific substance ka state is not heat energy. That's a thing. Okay. Okay.
So then, ma'am, what did you mean when you say that like they're at the same temperature?
So temperature is directly related to the internal energy, U. So heat energy can change the internal energy, which like that actually brings us to the next concept, which is the first law of thermodynamics. Okay. So internal energy is something that we discussed pehle, right? So internal energy is the inherent energy of a substance. So this is the inherent energy, something that's just there, like a substance exists, matlab uska ek energy value hoga. So that's internal energy. At a particular state. मतलब एक particular temperature पे, एक particular pressure पे, at a particular state. So internal energy is something we can measure. Okay, 30 degrees Celsius पे इसका internal energy क्या होगा? 45 degrees Celsius पे इसका क्या होगा? 120 degrees Celsius पे इसका क्या होगा? So internal energy is a state function. Okay. And this is represented by U. You will also see some other international textbooks being using E for representing internal energy. So either U or E.
Ma'am, how did we conclude that internal energy is a state function?
Because it is something that gives you an indication at a particular state. Like heat energy, heat is something that's given out. Again, when we talk about heat, it's like heat is released or heat is absorbed. कुछ तो source चाहिए होगा. It is a process of something being heated up. उसका temperature अगर increase हो रहा है तो. Internal energy is just like how we measure the temperature at a specific temperature, uska ek specific internal energy hoga. So it's like describing the state of a substance at this particular point of time, at this particular pressure, at this particular temperature. वैसे. So internal energy is something that's used to describe the state. Heat, you don't say water ka heat kitna hai. You'll say water ko heat karo. Like you can heat water by giving it energy, either from a heat source or by like doing work on it, like different. Again, that's the path function, heat, when we talk about it. It's a process ka description. This is like an inherent property of an object. If I have an ice cube, uska ek internal energy hoga, like each of the molecules. So internal energy is a result of the kinetic energy of individual molecules and some other things that we can't actively measure or we can't see. Like it's just associated with the existence of the matter itself. And it's directly related to the temperature. Like zyada temperature hai matlab zyada internal energy hai. Something is at a lower temperature, it has less internal energy. That way. So it's represented by U or E. And of course, it's an extensive property. It depends. If I have like 1 kg of oxygen, that has more internal energy than 500 grams of oxygen. Simply because there are a lot more number of molecules. So lot more motion, lot more kinetic energy that way.
What's the first point under internal energy?
So internal energy, it's the inherent energy at a particular state. This is a state function, just like pressure, temperature, FUNC. Yeah.
Oh, okay.
So internal energy, like once we start talking about internal energy, we're going to talk about the first law of thermodynamics. It's directly related to that. So first law of thermodynamics is basically a relation between the internal energy, work, and heat. So once you're all like done with this, then I'll talk about the first law. Okay,
Ma'am, the quantity is necessary for this is because more the heat
Heat.
Well, how is the
So internal energy is due to like the inherent nature. Like one example is the kinetic energy of the molecules itself. That is one component of internal energy. So suppose I have 6 molecules here and I have 9 molecules here. Both are at the same temperature, same pressure, same conditions, same everything. So in which case, like when I calculate the total kinetic energy of each of these molecules, in which case is it going to be greater? Rishit,
9?
in this will be greater, right? So why do you say 9?
More particles.
There you go. So that's why internal energy is dependent, or it's affected by kitna quantity of the substance is there. So that's an extensive property. Sanskriti, you've been relatively quiet. You following like what's happening? Okay.
Ma'am,
Yeah.
you were explaining extensive property. I had the same doubt, but then I got disconnected. Could you please explain that again? I'm sorry.
So extensive property is like a property that's affected by the quantity of the substance. No, like I wouldn't say dependent, but it's like a property that is greater when there's a greater quantity of the substance. So internal energy is basically like the inherent energy of these individual particles and like the interaction between them and all of that. So if I have 6 molecules in a container versus 9 molecules in a container, when you add up all of the energies of these individual particles, in which case are you going to have greater quantity of energy?
The second one.
That's why it's an extensive property.
What are those particles? Like?
Atoms, molecules, ions, whatever substance, whatever it's made up of.
Ma'am, and shouldn't all substances have an extensive property? Like depending on the number of atoms, they will obviously have more energy, right?
Yeah, that's why internal energy is an extensive property.
Okay, so yeah.
So things like number of moles, mass, volume, these are all extensive properties. But when it comes to something like density, concentration, temperature, they're all internal. Rishit, you're asking what is inherent energy? Inherent, have you come across the word inherent? Like it's something that's, what other word can I use? Intrinsic. Like it's the nature of the substance. Like if the substance exists, it's there. Inherent nature. It's like metals ka inherent nature is to be hard and shiny. Like that. You can use inherent. Magnet is magnetic. Yeah, you call a magnet because it's the nature is magnetic. That's an inherent property. Yeah. Clear. First law of thermodynamics is something that you guys have known, used, very familiar with. What is the first law of thermodynamics?
Conservation of energy.
Yes. So one way to put the first law of thermodynamics is the law of conservation of energy. Do you guys remember what is the law of conservation of energy?
Energy is neither created nor destroyed. Total energy in a system remains constant.
Correct. If you extend this is something that's going to blow your mind. The whole energy that's present in the universe is always a constant. Like right from Big Bang till now, whatever energy is there in the universe, it's always been that. So yeah. So that's other ways to, like, I can see alternative statements here, but that's gonna introduce a lot of other things that are not gonna perpetual motion machine. Yeah, that's okay. Transformation of energy.
Have you like skipped heat capacity?
Yeah,
I think we have heat capacity, and after that,
no,
directly from
I checked.
6.4.
No, I you don't. I checked the thing. Heat capacity, specific heat capacity. That part is not there.
For us, our ma'am did a heat capacity, and then directly from whatever is 6.4 in NCRT.
I have to open the textbook for that. Rishabh 6.4 and all. I have to look at it. Calorimetry to nahi hai. Heat capacity is also not there. Like it was literally given in CBSE ka circular that heat capacity, like amongst the deleted portion. So I'll refer to it once again and I'll come back to it. Like whatever we do rest of the time, it's not really related to heat capacity. You don't really need to know it. So it's okay. We can do it again later. Okay. I'm going to get to the enthalpies really, like I want to do that because that's the bulk, the meat of the chapter. Like a lot of questions will be dependent on that. Okay. So first law of thermodynamics is basically your law of conservation of energy. Energy is neither created nor absorbed. It's just transformed from one form to another. So how does this apply to our current situation where we talk about heat, work, internal energy of a substance? Suppose let's say I have a container, it like constant volume, like volume may be variable, whatever it may be. So at situate, like it is at in the state A, like when it is in state A, let's say it has like a certain amount of internal energy. So basically at pressure P1, V1, T1. ठीक है, हमने कुछ process किया, like we have tampered with the piston, we gave it heat energy, whatever the case may be, and then it has gone to a state B. So when it is at B, internal energy है इसके पास U2, pressure हो गया P2, volume हो गया V2, temperature हो गया T2. ठीक है. So if the internal energy has changed, U1 से अगर U2 बन गया, then so let's say the change in internal energy is equal to delta U. Delta always preferred changes, internal energy is U. So if the change in energy is U1 to U2, again, we're talking about change in energy, right? Abhi, according to the first law of thermodynamics, this extra energy can't come from anywhere. And if at all it has reduced, it can't just disappear off, right? It needs to be converted to something. Agar humne energy diya, तो there should be a source for that energy. And if the system has given out energy, then that should have been transformed into either work or it must have released it as heat energy, right? So the two possibilities are, so this change in internal energy will be equal to Q, either heat has been like radiated out or it must have gone out as work, Q plus W. So this is like the mathematical form of the first law of thermodynamics. Change in internal energy is always equal to Q, if at all there's been heat released or heat given to the system, plus work, if at all there's been any work done on the system or by the system. So this is the mathematical form of internal energy. So energy is conserved. whatever change in energy has been there in the system, U1 say U2 delta U hua, that will be equal to whatever caused that energy change, either in terms of heat or in terms of work done. It is not always the case कि हमेशा heat has been released or given out. It's not always the case that work is done or done by the system or on the system. Generally, this is the overall equation. Now there's specific cases to it. Suppose it's an isothermal process. Then what does an isothermal process mean? What happens in an isothermal process?
No change in
No
temperature.
change in heat.
Temperature constant.
Temperature is constant, right? So temperature constant matlab, like this means delta T will be equal to 0. So if delta T is equal to 0, which of these three will be unaffected?
Work done.
We literally just studied work done is mechanical work. इससे कोई temperature का कोई लेना देना नहीं है. It's P delta V.
Pressure.
Huh?
The pressure.
Pressure may or may not be affected. Which of these three will be unchanged, Kaveri? We're focusing on these three terms now.
Or Q, the heat.
No, again, Q is like heat given or heat absorbed. Like that has, so decouple temperature and heat energy. Like, yes, heat energy can affect temperature, but work also can affect temperature. Temperature is something that's a property of the system. Heat energy is something outside, either you're giving heat energy or you're taking away heat energy. So separate both of them in your head. Temperature is a direct relation to the internal energy, you guys. I've been saying that like all the time since yesterday, ever since we talked about internal energy. Temperature, matlab, we're talking about the internal energy. Always, always, always. If there is an increase in temperature, it means that internal energy has increased. And the other way around, internal energy increase hua matlab, we see it in this thing as an increase in temperature. Okay, so if delta T equal to 0, which out of these three things will be affected?
Q.
Again,
No.
temperature may change nahi
Will
hogi.
it be constant?
What will be constant?
Delta
Delta U.
Delta U will be constant. It will be equal to 0. No change in temperature matlab there's no change in the internal energy of the system. Temperature is a direct measurement of internal energy. It's an aspect of internal energy. So internal energy, you can't physically measure kinetic energy of every single molecule, bond energy jo bhi hai, electronic repulsions jo bhi hai. It is impossible to measure this physically, right? So what we see it as in the real world is temperature. If you're talking about temperature, think of internal energy. So these two have a direct relation. Here, so if delta U is equal to 0, this means that this equation becomes Q equal to minus W. So physically what this means is, if it's an isothermal process, if at all you supply any heat to it, and if your temperature is constant, none of the energy has gone into increasing the internal energy of it. So all of that heat energy is converted into the work done by the system. Okay. So all of the heat energy is converted into work done. Q plus W equal to 0. Got it? Like, makes sense? So
Oh, ma'am.
Hmm.
is equal to minus W. Could you explain that?
See, isothermal process है, मतलब temperature में कोई change नहीं है. No change in temperature means no change in internal energy. This is like the relation
that-
between these two is constant. That's it. So apply that in this equation, our main equation. So delta U 0 हो गया. So Q plus W equal to 0. So that I wrote as Q equal to minus W.
Achha, you just substituted. Okay.
So this Q is heat energy. W is work done. So what this means is whatever heat has been supplied is all converted to work, or whatever work has been done is converted to heat. So nothing has gone to the internal energy of this thing. That's why delta U is 0. Okay. Similarly, let's say it's an adiabatic process. So adiabatic process, what do you know about adiabatic process?
With the
Transfer of heat.
Q will be 0 then.
Correct. So adiabatic process may there is no change in heat, like heat is not given out, taken in. So adiabatic process Q equal to 0. This means delta U is equal to W. So whatever work has been done is converted to internal energy. The other side of things, like uska reverse, like whatever change in internal energy has happened, that is equal to work. So now change in internal energy, agar ye negative hua, to work done is negative, so work is done by the system. Then delta U positive hua, like temperature has increased. Matlab, huh?
We are listing all these things right now. Those are what, like properties of the law? Like what?
Consequences. Like this is our main law. This is the first law. So we are applying it to different situations. So if it's an isothermal process, then what can we infer from the law? If it is an adiabatic process, then what can we say about the law that way?
So basically, like for different situations, we can find through different equations.
Yes. Cases. Yeah. So the third case, if it is a gaseous system, like in a gaseous system, so in a gaseous system, let's consider the case where a gas expands against a constant temperature P. So gas expand हो रहा है. So if a gas is expanding, work is done by the system or on the system?
By the system.
There you go. Work is done by the system. So work done by the system, or in this case by the gas, will be equal to minus P delta V. So our first law changes as delta U will be equal to Q minus P delta V.
Excuse me, ma'am, can you go to the last slide? I got disconnected.
Yeah.
Ma'am, is it possible for you to explain the third point again?
Yeah, I will be going over the third point because that leads us directly into the concept of enthalpy. So once you're all done with it, then I can do that.
Ma'am, how many laws of thermodynamics are there? 3.
Yeah, we have 0 at first and second. Guys, make it quick. Done. Smira, Sanat, Kaveri, Arnav, Rishit, Sanskriti. Sanskriti done? Okay. All right. So third point, I'll take it as a fresh case because we'll be doing the same thing again later. Okay. So suppose consider a case.
Could you go back? Like, I just wanted to write the formula. And not this, you just
I cleared it. So we'll be doing that. That's what I just said. We'll be deriving that again. So the third case that I took was, let's say gas expands against constant pressure. I'm just going to build up a little on that. Consider a case where, like, if QP heat, this much amount of heat was absorbed by a gas at constant pressure. ठीक है, अभी constant pressure being the keyword. So heat absorb हुआ, मतलब temperature has changed. Heat absorb matlab, and I'm not saying this is an isothermal process. I've just given heat to a gas. Like I've taken some gases in a beaker and I've given heat to it. So consequences, QP heat is absorbed matlab temperature. What will happen to the temperature of that gas?
It'll increase.
Increases, correct. Iska matlab in terms of our energy, focus on the equation delta U equal to Q plus W. तो अगर temperature increase हुआ, इसका मतलब what aspects will be affected?
delta U.
Delta U is affected. So delta U increases. Okay. Increases nahi, like there is a delta U has a positive value. Let's say U increases by delta U. Like delta U change hua utna because of the heat supplied. Also, constant pressure, temperature increased. What else would increase of a gas? Like remember, apply your gas laws. If T increases at constant P,
Volume.
yes, then volume also increases. तो constant pressure पे volume change हो रहा है, इसका मतलब there is work done by the gas. Tell me if this part makes sense.
I didn't get it. How is the pressure constant but then volume increases?
If temperature increases at constant pressure, then gas loss. Rishit, got it? What happened?
Yeah, I got it.
Volume increases, VT, Charles law. So imagine piston hai. So as temperature increases, pressure is always constant. So volume is increasing. So the piston is being pushed upwards. So if there is motion, like as long as there is a change in P and V, there is work done by the gas. Because gas is the one that's like pushing against that pressure while expanding. So basically, delta U will be equal to the heat that is supplied and work is done by the gas. So instead of work, I will substitute QP because at constant pressure minus P delta V. This much amount of work is done by the gas. Work is done by the gas, इसलिए ये negative है, and volume is expanding. So if it has changed by delta V amount, because of delta U change in pressure, because I give QP amount of heat, so it's P delta V. So I can write this as U2 minus U1, because that's change in internal energy, is equal to QP minus pressure constant here. So this will remain P, V2 minus V1, right? Final minus initial. Or this is QP into minus PV2 plus PV1. I've just multiplied it. Now this, I can rearrange it as QP equal to U2 plus PV2 minus U1 plus PV1. Take a minute, do the rearrangement on your own, check the plus minus signs and tell me once you've like gotten till here. Till here, it's all mathematics.
Ma'am, I know I've asked this before too, but I still didn't get it. I know Charles' law says temperature is directly proportional to like volume. But even if the pressure is constant, how does the volume increase? Like then isn't pressure gonna decrease too?
We are keeping the pressure constant. So the specific point of pressure being constant is important because we are basically applying, like this is a case in our real life situation. So around you, whatever process happens, like if you're boiling water, or if you're doing a reaction in a test tube or a beaker or something, the pressure is always atmospheric pressure. 1 atmosphere to maintain ho raha hai na, unless you're taking it to an extreme case where you're sealing it from all sides, you're closing it, you're putting it in a vacuum chamber, like unless you're taking it to the extreme, a lot of natural processes that occur around you, the reactions that you do, are always happening at constant pressure, which is your atmospheric pressure. That is the reason we took this constant pressure case. And generally, even if you were to do it in reaction vessels and all, you will take it to that high pressure, whatever is required, and then you're going to like maintain that pressure more or less. Okay, so that's why the constant pressure part is important. So this is a given, Rishit. So I'm saying that I'm keeping pressure at this much value no matter what. I'm adjusting the condition so that the pressure is always constant. So in that situation, if I increase the temperature, like think of your hot air balloon. If I'm increasing the temperature, then what is going to happen to the gas inside?
Sorry, could you repeat?
So if I'm keeping the pressure constant and if I heat up the gas that is inside, what will happen to the volume?
Volume would increase.
That's what I've written here. That's what is happening. Volume increases. There is a change in volume. That means work is done by the gas. Okay. Also, guys, I don't see a lot of submissions that are happening, like do you do the work after the end of the chapter? Do you solve questions?
Yes, ma'am. But like sometimes it takes me a lot of time, and like by then there's like a different picture up.
Okay. So in that case, just communicate with us now. Like, okay, more than half of this is left. If it's taking a lot of time, we can look into why it's taking a lot of time. We can work together on that. But if I don't know if there's any work going on from your end, it's going to be difficult. And that's the whole reason. Like, there are a lot of like physics may it's a direct, building up of the previous concept. In chemistry, there's a lot of intermixing of concepts. Like we are talking about a lot of gas laws in thermodynamics, even though it was a previous chapter. And we always keep coming back to your chemical bonding when we're talking about organic, inorganic. Whenever we talk about any sort of bonding, we'll look at concepts from that chapter. So it's quite important that you keep constantly revising these chapters. And if you want to, have it at your fingertips, be good at it, be able to follow the current concept, you need to build that base. Like once it's taught in class, if you leave it after a week, things are going to like just look at literal Latin and Greek, because that's what we use, the words and variables. So constant revision is necessary. I think each of you, when we did that one-on-one counseling also, 2 days for each subject, spend that time, ensure that, see, doing questions is what will help you gain clarity also in the concept, rather than just passively listening to what a teacher is saying or reading what is there in the textbook. If you grapple with it, you'll get like proper clarity, because you're the one using your brain and trying to, twist it and fit it to, the specific situation given in the question. So it's quite important to keep revising. Okay. Because we're already behind. Like in your school, you already started equilibrium, inorganic B, 4A. I can't keep repeating the previous concepts again and again. Like I'll need some amount of work that you guys also do. Okay. All right. Tell me if you have like reached here, final step.
Reached.
Understood?
ma'am.
Were you able to get it? Ki plus minus kya kiya humne? Did you work it out?
Yes, ma'am.
Okay.
Yes, ma'am.
ठीक है. Sanat, Rishit, Kaveri, Sanskriti.
Yeah, done.
Yes, ma'am. I'm done.
Okay. Okay. So observe this. I'll start it in the next page again. So the whatever heat energy that we have given has been used to change the state of a substance. Pehla state tha. So it's been used U2 plus PV2 minus U1 plus PV1. So whatever heat energy we gave has been used to change the state of that substance from this particular state to this particular state. Pehla internal energy U1 tha, and it was at pressure P with volume V1. That changed into internal energy U2 with pressure P and volume V2. So the total of, this particular sum of internal energy and the capacity to do the mechanical work, U2 plus PV2, is defined as enthalpy. So this, I'll bring in the new variable, write it as H2 minus H1. So this new variable H is what is enthalpy. Okay. So enthalpy, if you look at formal definitions, this is basically the total heat content at constant pressure. Okay. So not to be confused with heat energy. So enthalpy may, we are taking into account the internal energy, like the one that's causing temperature and all of that. And also we are we are also taking into account the product of pressure into volume. So both of them together is enthalpy. And because enthalpy contains internal energy, we cannot measure the exact value enthalpy. We always deal with delta H, which is change in enthalpy. Okay. So whenever we do a process, some of it goes towards changing the temperature of the system. Some of it goes towards, like expansion of the gas or compression of the gas. So it's the total of both internal energy and the work done is what we consider as enthalpy. Yeah, Sanat, what's up?
So is enthalpy like a type of limit?
Limit in what sense?
Like it's a limiting boundary kind of thing. You can only have this much heat in a particular substance or in a particular gas.
No. If I give it a lot of heat, if I continue to give it heat hypothetically, uska enthalpy will keep on increasing as the internal energy keeps increasing and as its volume keep increasing.
But like if you keep giving it heat, then the pressure will also change, right?
That's the thing. Like it's the total heat content at a constant pressure. And limit, I mean, practically speaking, if you're on Earth, there is going to be limit because of all the other things involved. But theoretically, like hypothetically, you don't really would have like any limits as such. So enthalpy is
Okay.
a state function because it's a function used to describe ki total heat kitna hai usme. So because you can see it is sum of internal energy plus, because it is sum of internal energy plus pressure volume product. So all three of them are states. So enthalpy also ends up being a state function. It's kind of like hard to get around because it's not like a physical equivalent that I can show you guys what enthalpy is. But the idea is that it is like the total heat content. Like if I'm giving heat energy, kuch process ho raha hai, and there is a change in the state of that system only because of that process. So if we have to nitpick, there is change in temperature represented by internal energy. There is a little bit of expansion represented by the PV work. So it's like all of these put together that counts under enthalpy. Okay. So delta H is equal to change in internal energy plus P delta V. And the reason why we bring in enthalpy is because it's easy for us to make like use, because every time whatever process we do, there's going to be a little bit of change in temperature, there's going to be change in the volume. So instead of having to add both of these at all times, we just count enthalpy as a single function and then we just use that. Okay. So a result of this particular thing, so basically if heat is supplied, write in a different. So if heat is supplied at constant pressure, then this is going to result in change in enthalpy. Because constant pressure hai, So I'm supplying heat, matlab it is free to increase the temperature, it's free to expand the gas. Like dono ho sakta hai. So overall change, there'll be a change in enthalpy. And if heat is supplied at constant volume, then what will this result in a change? Like what is the change that this will result in?
Like the volume of the gas is increasing,
Yeah.
right?
Yeah, constant
The
volume.
enthalpy would be same. Oh wait, it's constant volume.
Hmm. So I'm supplying heat, think back, QP hai or volume constant hai. So it's not changing from V1 to V2. So what will this result in a change in or no change?
We will cancel out, right? Then U will be remaining.
Yes.
U2.
So that's a change in what is U?
Internal energy.
Of internal energy, right?
Yes. Yeah. So if I maintain pressure to be constant, उसमें volume भी change हो रहा है. So there is a work done aspect there. So you'll find change in enthalpy. So enthalpy is internal energy plus the work done aspect. And if I'm keeping the volume constant, so there is no work done. So whatever change heat I'm supplying, that is utilized only to increase the temperature. So you'll find change in internal energy. Okay. Now, if you look at it, how we got the expression?
1 second. I'm
Huh?
just like writing the last part.
Okay, okay. All right. Let me know when you guys are done. And we'll clear.
Ma'am,
Hmm?
just asking if it is constant volume, so delta V will be equal to 0.
Hmm.
Okay.
Right. So Kaveri Sanskriti. Yes. And Rishit, let me know when you're done.
Ma'am, I'm done.
Okay. Cool. So if you look at this, I have specifically considered heat absorbed by a gas. And because we have considered it as a gas, we said, okay, there is expansion and all of that. Now, what if the substance was a solid? So what if it was a solid or a liquid? उसमें कोई mechanical work का concept हो सकता है क्या? Do they change volume when you give them heat energy?
Yes.
Yes. If you compare it with gases, how much is it?
Uh, Very negligible for
Negligible.
solids at least. For liquids, it will be slightly more.
So for practical purposes, in the case of solids and liquids, whatever change in enthalpy is there, that's almost equal to change in internal energy. So only in the case of gases, we take delta H equal to delta U and we count this pressure into volume difference factor. Okay. So another application of this change in enthalpy thing, when we look at a reaction, like if not a reaction, let's say a process. So let's say in a process, initial case में, let's say there's Na moles of gases occupying Va amount of volume. And final, like process ke end mein, be it a reaction, if not a reaction, it may be something like conversion of water into steam or mixing a lot of gases together. ऐसा भी कुछ हो सकता है. Let's say this got converted to, there are end of the process, there's Nb moles occupying Vb volume of a gas. And this, of course, we are considering at constant pressure and temperature. Let's say, for example, chemical reaction. Or it could be like mixing up of gases, like koi bhi process hai. But initially, when you measure this Na moles and Va volume being occupied, finally process ke baad, there's Nb moles of a gas occupying Vb volume of this thing. Now,
What have we written outside the bracket?
oh, this is at pressure P, temperature T.
Oh.
Like these are constants. Pressure, atmospheric pressure maintain कर रहे हैं. Let's say random temperature, room temperature पे ही हो रहा है. Now, change in enthalpy is delta U plus P delta V, right? Keep this aside. We're going to apply our particular situation to this. So let's look at, see, at constant temperature hai, so delta U is going to be wait, this is not really making any sense. Anyway. What is the point that this is trying to make? No, like, let's, like, this is not making any sense. I don't see a context of why should this be also. Oh no, yeah, now it makes sense. Okay. So this is the expression for this. Let's focus on change in the work done here. So initially PVA equal to Na into RT. And finally also gas equation PVB equal to NB into RT. अभी अगर P delta V find out करना है, this is basically equal to PVB minus PVA, like the final conditions minus initial conditions. So just substitute it, you'll get it NB minus Na times RT, which is delta N RT. Or delta N G Let's call it delta Ng, because we are only counting the change in the number of moles of gases. Solids, liquids we don't really they don't really exert, like occupy volume, exert pressure, so we don't really care about them.
Ma'am, could you repeat what Ng was?
Ng is the
I didn't get it.
change in the number of moles of gases specifically.
How are they creating matter?
How? Matlab?
Won't the like total number of moles be constant?
No. Think of this situation. Do you remember the reaction for combustion of methane?
Yes, ma'am.
CH4 plus O2 gives CO2 plus H2O. Can you balance this equation? Or wait, this was the wrong example. Let's not go with this. Think combustion of coal. C plus O2 gives CO2. यहाँ पे
So
the
like how many moles of the new gas?
oxygen. Yeah, this is also like, okay, equal ho gaya number of moles, but you'll come across formation of ammonia. N2 plus 3H2 gives 2NH3. So matter is conserved because this is a balanced equation. But what is the total number of moles of gases on LHS?
1 and 3.
4.
And product may total how many moles of gases do I have?
2.
So the number of moles of gases has reduced. Like reactant mein mere paas 4 moles the, but after the process I only have 2 moles of gases. So delta Ng is 2, or rather -2, because it's reduced. So that's what it means. So it's not violating the law of conservation of mass as such, but the number of moles, like the constituents, can vary, right? And if you think back to Avogadro's law, it doesn't matter which gas it is. The only relation is, okay, if I have 2 moles of a gas, it doesn't matter if it's 2 moles of nitrogen, hydrogen, or ammonia. It's going to occupy this much volume at this much temperature and pressure, which is why it like kind of works. You just worry about the number of moles. Doesn't matter what specific gas we're talking about. Okay. Does this clarify, Ritu?
Yes, ma'am.
Okay.
So then delta H will be equal to delta U plus delta NGRT, right? You just put the value.
Correct. That's what we're going to do next. Rishit, you just asked to repeat this. Can you be a little more specific? What part did you not get, or what question you have? Which part should I repeat?
Why did you suddenly use the ideal gas formula?
Because that's how volume, pressure, and number of moles are related. Ideal gas gives you the relation between that. So I wanted to find the relation between the change in number of moles at the specific pressure when the volume is changing. Okay. So substitute this, P delta V is basically this. So delta H is equal to delta U plus delta Ng RT. Okay.
Also, ma'am, could you just repeat the solids and liquids part? Like, how did you get it approximately equal to delta U?
Solids, liquids, like, can you define expansion or change in volume for solids and liquids?
Expansion or?
Or like in general, a change in volume in the case of solids and liquids?
No.
So which is why you end up having the change in enthalpy approximately equal to the change in internal energy itself. if at all there's like a temperature difference and all. But it is like properly defined in the case of gases because this value matters a lot more significant.
Volume as in like what it is occupying.
Yeah.
Can't we tell like there is, for example, water in a container, and then you just throw some water out. We can see how much the volume has decreased of it occupying, right?
So accordingly, the delta U is also changing, right? Because you're literally removing the so many number of particles. Okay. At least let me know if that's like convincing, if you followed, if that answered your question. Don't just be silent because I can't even see your face.
I'm just thinking, I'm just thinking how that is possible. Like that will change, right? Delta U, but can't we calculate the V as well?
Yeah, but again, it's not delta U plus delta V alone, right? So this is the work done because of that expansion or contraction if it's work done on the system. So there is a P delta V aspect to it. So like even in the case of ideal gas laws and everything, we define it for gases because it doesn't make sense physically in the case of solids and liquids. Solids and liquids, volume is always going to be constant. Only if you raise the heat, that too on a very, very tiny scale. That's why I didn't say it's completely equal also. It's just approximately equal.
Because like gases, the number of molecules or atoms remains the same, but as we compress or expand it, that is what changes. So that is why we use it in gases.
It's more significant in gases. In solids and liquids, the expression mathematically it remains the same, but it's almost equal. Like it doesn't matter if that particular term is there or not there. That is why we ignore it, practically speaking. In gases,
So
it becomes more significant.
like as I said, so since we are removing the liquid itself, we are changing the quantity, but in gases the quantity remains the change. I mean constant, but we like kind of either contract it or expand it depending
not-
upon the situation. So that is why that is more significant.
No. So in gases, irrespective, like you still can change the quantity of gases and delta H, delta U, these values will change. But in gases, even if you don't change the quantity, the P delta V will still remain significant. So it matters in gases because gases have a property of expansion and diffusion, which solids and liquids don't have.
Okay.
All right. So coming back to this, delta H equal to delta U plus delta NGRT. So depending on the change in number of gases, actually the examples we took earlier matters. So suppose I have combustion of coal, C plus O2 gives CO2. Abhi LHS or RHS, dono side there is 1 mole of gas only, which means delta Ng is equal to 0. So based on what sort of a change it is, like if there is a change in the number of moles of gases, you can kind of predict the relation between delta H and delta U. So if delta Ng is equal to 0, like if there's no change in the quantity of the number of moles of gases, then delta H is equal to delta U. Then if there is a small change, like if this is greater than 0, so if the number of moles of gases is increasing, then the change in enthalpy, delta H, will be greater than delta U. And if the number of moles is decreasing, then delta H will be less than delta U. This is just taking it one step further, defining the relation between the change in enthalpy and change in internal energy based on the change in the number of gas molecules. Right. So once you're done, we'll talk about enthalpy. We need one more session. All right, everyone done? Okay. So now that we've had like an introduction to enthalpy, the reason why enthalpy is important is all of our chemical processes, whenever we talk about energy changes. Now, this is something that you all would be familiar with. We talked about ionization energy, like exothermic, endothermic ke case mein, those energy changes, how much heat is released by the reaction and how much heat is absorbed by the equation. Latent heat of fusion, latent heat of evaporation. So whenever we talk about all these energies, what we are referring to is basically your enthalpy. So enthalpy is the correct word to use in these contexts, in these situations. Okay. So in chemistry, like this is what, so thermodynamics, like there's a lot of directions you can go in. We are going to study the parts that are relevant for chemical processes. Okay. So thermochemical reactions. Okay, enthalpies. So different types of enthalpies that we come across in thermochemical reactions. So before we get into the different types of enthalpies, there's a little bit of basics that let's discuss about. So there's something called heat of a reaction.